Okay, so we started talking about Jacobian matrices last time. Let me just remind you what the context is, what we're doing with Jacobian matrices, what we found in our discussion of differentiability last time. There's lots of different ideas related to differentiability, different kinds of ways to think about derivatives. We have directional differentiability, directional linearity, all these different forms. But differentiability is the big one, and if a function is differentiable, then nice sophisticated things we can't talk about happen, but more practically, you can compute directional derivatives with a linear transformation. And it's called the derivative transformation, and that is the linear transformation that we study with Jacobian matrices. Specifically, that linear transformation is represented by a Jacobian matrix. That's the definition of the Jacobian matrix. So the Jacobian matrix represents the derivative transformation. The derivative transformation lets us compute directional derivatives. So it's still all about directional derivatives. It's still all about a relationship between input vectors and output vectors. Right? That hasn't really changed. Just that we have a more powerful and sophisticated way of getting our hands on them now. So we went through a wonderful calculation last time that uses a lot of different facts that we've talked about in this course. That shows a punchline, really nice punchline, which is that the Jacobian matrix is simply made up of partial derivatives. So the most sophisticated and powerful way that we have to think about derivatives of multivariable functions can be computed with the world's simplest and easiest to compute ways to think about derivatives, namely partial derivatives. Everyone's favorite kind of multivariable derivative, because not only is it familiar in the form of single variable differentiation, you get to just pretend that large parts of your function are constant while you're doing it. So the world's easiest derivatives to compute, and you assemble them in this way, and they give you the most powerful, sophisticated point of view on derivatives. So lovely, lovely little result there. Okay, so let's do some examples. I'm just going to do two quick examples. There are several more examples that you can look through in this section. I encourage you to do that, but I'm just going to show you two of them. So start with this one. Here is a function, 2 input variables, 3 output variables. And the question we have is, suppose we're at this point in the domain, and moving with that velocity vector, how would we compute this directional derivative? So what's the velocity vector for the output of the function? So directional derivative. Now, you could take a 4.3 point of view on this problem. It's just asking for a directional derivative, right? And you can parameterize the line and plug into the function and multiply and take the derivatives, etc. So a fair amount of algebra would be involved with that. Especially look at these functions. Each one's a product, so you're going to have product rule stuff to deal with, and there's trig and cubes. We could do it, but it's all else being equal, kind of maybe nice if we didn't have to. So what we're going to do instead is first observe that directional derivatives can be computed with the derivative transformation. Right? That's what the derivative transformation is for. The function's continuously differentiable, and therefore we can talk about the derivative transformation. Secondly, we can compute the derivative transformation using the Jacobian matrix. That's what the definition of the Jacobian matrix is. It is the matrix that lets you use this sophisticated tool. And the Jacobian matrix is made up of just a bunch of partial derivatives. So let's compute this Jacobian matrix. Keep in mind, let me flip back here, each column of the Jacobian matrix is a partial derivative of all the different components of the function with respect to a particular input variable. So this first column is the partials with respect to x1. Let me zoom in to make sure this is clear. So first column, partials with respect to x1. The second column is the partials with respect to x2, etc. So each column corresponds to an input variable. Okay, so let's do it. So let's compute this first column of the Jacobian matrix. The first column is obtained by taking the partials with respect to the first input variable. So in this case, then, we just want to take these three components and take the partials with respect to x. That's easy. Sine y. Let's see here. Negative y sine x and 2xy cubed. Easy partial derivatives. There you go. Right. The second column is going to be computed by looking at the partials with respect to the second input variable. So now let's take the y partials of these functions. Easy partial derivatives. You guys can do those on your own, and that gives you this second column. So in terms of the the taking of the derivative, the main part of the algebra that goes into these kinds of problems, look how easy, right? Really easy to just write those down. All right. So, so what do we do with these at this point? Now keep in mind the Jacobian, we've taken the derivative, the various derivatives of that function, but specifically we're interested in knowing the what this directional derivative is at that point. So we've got to plug in that point, pi comma pi over 2, into that matrix. And altogether then, at that point, the matrix has those values, and that's again just a plug and chug. Plug in x equals pi, y equals pi over 2. Remember your values of the trig functions, etc. And so this then is the matrix that we multiply by that vector, and now it's a fairly easy little arithmetic problem, and there's your final answer. So it's a very streamlined process, right? A few easy partial derivatives, you plug in some numbers. Everybody see how this works? Very powerful idea. All of this came out of our initial observation at the start of last lecture that weirdly, in a lot of cases, surprisingly large number of cases, directional derivatives happen to be a linear function of the velocity vector. Now remember, that was our very first observation, and that is what snowballed into this very powerful result. Okay. Right. Another example. This example y'all can read. It's a variation on the one we just did. Another example. Now, new function. This one's function from R3 to R2. So there's 3 input variables, 2 output variables. We're going to compute the directional derivative again. By the way, this is a rehash of the example 4.3.2, so you might compare what we're about to see here with example 4.3.2 from several sections back. And we did it sort of the brute force way back in section 4.3. Here we're going to do it the new powerful way using Jacobian matrices. So as usual, I can compute a directional derivative with the derivative transformation. The function's continuously differentiable, therefore differentiable. Derivative transformations are evaluated with the Jacobian matrix. Jacobian matrix is made up of partial derivatives. So one column at a time, let's compute this Jacobian matrix. The first column comes from taking partials with respect to the first variable. So we're going to take x partials of these two functions, and that's y and 0, as I have here. Second column comes from taking partials with respect to the second variable. So y partials of these two functions, x and z, which is, again, what we have here. And then likewise for the third column, z partials. So the differentiation part of it, what you might call the algebraic side of it, is really easy. Now we've just got some numbers to plug in. We plug in the point that was given in the original question, and the matrix turns into this. That's what we multiply by the velocity vector, and altogether we're trying to compute ends up being 5, 6. And you might recognize those numbers. This is what we determined in that previous instance of this example. So which do you like better? I have a strong preference for this method. Right, it's really much less trouble. My inner lazy mathematician thinks this is great. Everybody happy? Okay, so that's all I'm going to do. There's another couple of examples here. You guys can read through them. They're just variations on the same idea. And so I'm going to move on now to the next section and talk about a very closely related topic of gradient vectors. Okay. So with gradient vectors, I want to talk about a special case of what we just talked about. What we were talking about was, how can we compute directional derivatives if the function is differentiable? If the function is differentiable, let me just remind you. If the function is differentiable, you can compute directional derivatives with the derivative transformation, which has a Jacobian matrix, which is made up of partial derivatives, and you can turn that inconvenient problem into a really easy problem. So differentiable functions are great, and it boils down to the fact that the Jacobian matrix is easy to write down and easy to compute with. Okay. So now here I'm considering a special case where we're looking at a real valued differentiable function. So real valued, keep in mind, just means that the output is a real number, a single real number. Well, being as it is a single real number, each of the several input variables, partials with respect to which give you several different columns, each one of those has only a single entry because we're taking the partials of the function with respect to each of these several input variables, but the function only has one entry, and so each column only has one entry. Said differently, this matrix has a single row. All right, does that make sense to everybody? Everybody see the sort of the idea there? And this is a weird fact, but it happens when you have a real valued function. By the way, in general, for all different kinds of multivariable functions, the number of output variables, so the dimension of the target, is the number of rows in the matrix. The number of input variables gives you the number of columns, sort of by construction. The number of output variables gives you the number of rows. Nice fact. Okay. So, so here's what our directional derivative computation looks like. Directional derivatives are computed with the derivative transformation. Derivative transformation is computed with the Jacobian matrix, right? Familiar, we've been through this a bunch of times. The Jacobian matrix in this case looks like this. In particular, the Jacobian is this single row matrix. Fine, so what we're computing then, ultimately, in order to compute our directional derivative, we're computing this product. We have a single row matrix that is matrix vector multiplied by a vector. And here I'm going to make sort of a simple observation. It's like an arithmetic observation, but the way you multiply this matrix times that vector is a dot product of that dot that. And said differently, it's that times that plus that times that plus, that times that, etc., plus that times that. And multiply and add corresponding components. And I'm just going to rewrite that as an actual dot product. That times that plus that times that, etc., plus, whoops, color didn't take, there we go, that times that. So here I'm viewing it as a dot product of two vectors, whereas previously it was a matrix vector product. And algebraically, it's a different mathematical object. It's a different, technically, operation. But arithmetically, it's the same thing. Does everybody see how these are the same calculations? The difference then is that I'm choosing to interpret a matrix as a vector, and I'm choosing to reinterpret correspondingly this matrix vector product instead as a dot product. Now the question comes up, what's to be gained from this? Why would anyone ever want to? Clearly, this is an arithmetic triviality, right? So who cares? And there's a great answer to the who cares question, and that is, geometrically speaking, we already have a pretty good instinct for what a vector looks like. And this is one of our fundamental geometric ideas in the course. A vector, that thing has a direction that it points. Not so much with a matrix. Right? Furthermore, this dot product, we know all kinds of cool stuff about dot products. You might recall that we've had great success in the past when we were studying cross products by finding a way to relate, in that case, cross products to dot products, which we knew loads about. And that helped us learn more about cross products. So similarly here, maybe by getting dot product involved, which we know loads about, we might be able to learn more about the other objects in this equation, and that's what's going to happen. Okay. All right. It's going to turn out, along those lines, that this vector will be an important object of study, thought of as a vector. We call it the gradient vector of the function in question, evaluated at that point A in question. So again, it's just kind of a different way to write down the Jacobian matrix. It's morally kind of the same as the Jacobian matrix, just not thought of as a matrix, thought of instead as a vector, a geometric vector. Okay, so that's the term gradient. We're going to make some nice conclusions about how to think geometrically of the gradient over this section. And the notation, by the way, a little weird. There's this little symbol there. It's kind of an upside-down little triangle. It sort of looks like an upside-down Greek letter delta. There's the capital delta. Right, so this is not that. Make sure not to write it like that. Every so often I see a student writing it as it does. It's very... In fact, this is a different mathematical thing. This symbol written like that means something different. So it's written like that, and it's a way of representing the gradient. I'm going to say a few other things about that symbol when we get to Chapter 6. Okay, so let me just restate an old result. It's written as a new theorem here, but it's really just a different spin on an old fact. The result here says that directional derivatives are computed by dot products with the gradient vector. And, well, yeah, dot product with the gradient vector, the whole point of the gradient vector is that this construction effectively is just an arithmetic twin of multiplying by the Jacobian matrix. That's where we got this in the first place. So, of course, this computes directional derivatives. That's what the Jacobian matrix was for. So it's not really mathematically a new fact. It's just a twist on an old fact. Okay. Please do make sure to recall this only works for real-valued functions. Right? You have to have only a single output variable in order for the Jacobian to have only a single row in order to be able to rewrite the matrix product as a dot product. So this all hinges on it being a real-valued function. Okay. All right. So what? One more quick observation. Don't forget our Jacobian matrix looks like this. Previously, we had observed that the columns correspond to partial derivatives with respect to a single input variable. So if you'll notice here, this first column, for example, is all partials with respect to a single input variable. So loosely speaking, columns correspond to input variables. So we can now make another kind of cool observation, and that is, having assembled the Jacobian matrix like this, let's look at a row. Yeah, sure, green's fine. And what can I say about that row? Well, weirdly, every entry in that row is a partial of the same output variable. In fact, this row is made up of all of the different partials of that one output variable, f1 in this case, with respect to all of the different input variables. It's the gradient vector. Okay. One output variable and the partials with respect to all the different input variables. So it's just kind of an interesting twist on how to think about the Jacobian matrix. So you can think of what we talked about last time is you can think of the Jacobian as its columns corresponding to the different output variables, the partials with respect to the different output variables. The partials with respect to the different input variables. And now we can instead choose to view it as where the rows are the gradients of the different output variables. There's a different way to think about the Jacobian. Is everybody happy with that observation? Okay. Right, so now let's draw some geometric conclusions about the gradient vector. I want to come up to this picture actually and ask a question, pose an interesting geometric question. So I'm going to consider a function f. I'm looking at the domain here, so that means that our function f is doing this. So specifically, all of what we're going to be looking at is taking place in the domain of this real value function f. And I want to think about what's happening at a particular point, at that specific point A. At that specific point A, I can talk about what the gradient of the function f is at that point. Of course, the gradient is some vector pointing in some direction, whatever that means. Okay. So here's the question. The question is, of all the directions from that point, in which of those directions is the function increasing the fastest? And by fastest, I mean per unit distance that you travel. We have to talk about per unit distance, or said differently, we have to restrict our attention to unit vectors. Otherwise, the question becomes silly because if you're tempted to say, well, that's the direction that the function's increasing the fastest, then a smart alecky person can say, nope, it's increasing even faster with that vector. And then someone else comes along and says, no, even faster with that vector. It devolves into nonsense, right? So in order to avoid nonsense, we're going to restrict our attention to unit vectors. Said differently, we want to say per unit distance traveled from that point, in which direction is the function increasing the fastest. Does everybody understand the sort of the question? Okay. You could view this differently as, suppose we were looking at the graph of this function. So instead of domain here, target there, let's suppose that the domain is the xy plane, the horizontal xy plane, and then the output represents height, in which case the graph is a surface, some sort of a hilly kind of topographical shape. At a certain point, namely at a certain point on the side of the mountain, in which direction do you go for the function, namely height, to be increasing the fastest? Said differently, which direction do you go to go uphill? Which way is uphill on this mountain? Right? Certainly we've all had this experience, I suppose, I hope, of at some point having been on the side of a hill, right? And there's a very clear idea, no doubt in your mind, if you were to drop a beach ball, which way would the beach ball roll? That's downhill, right? Uphill is the way opposite from that. Does that make sense? Okay. All right. So the uphill picture is a reasonable picture to talk about. I like talking about the direction in which the function is increasing the fastest because it doesn't require thinking about the graph. Again, the graph interpretation is very limiting. You can really only do this, for example, this mountain picture, the graph picture, as it were, in the case of two input variables and one output variable. It's very limiting. So I want the primary point of view to be what direction makes the function increase the fastest. Okay, so let's try to answer the question. I'm going to consider a unit vector here and ask a very reasonable question of, well, what is the unit directional derivative in that direction? Okay. And let's compute it, and then we'll figure out how to optimize it a little bit later on. So, a unit directional derivative using this formula, dot product with a gradient vector. This is our sort of new point of view on it, so we're not going to think about Jacobian matrices and derivative transfer. We think about it as a dot product with a gradient vector. Okay, so dot product of our unit vector direction with the gradient vector. Good news, we know good stuff about dot products. Dot products are geometrically related to this expression, the product of the magnitudes times the cosine of the angle between them. Old fact, chapter 1. Okay. Good news, that unit vector has magnitude 1. So I'm just going to cross that off, and all that's left then is magnitude of the gradient times cosine of theta. So there's our answer to the first question, namely, how fast is the function increasing in that unit vector direction? U. Magnitude of the gradient times cosine theta. Now let's go back up to the picture. Let me zoom in again. There we go. So, given a direction, the unit directional derivative depends on that magnitude and that angle. And here's the thing: as I consider different unit vectors, there might be, maybe if the unit vector were pointing, that way, or all the different unit vectors that I might pick, the magnitude of the gradient is constant. It doesn't depend. It's stationary, right? It doesn't depend on which direction are you looking. The magnitude of the gradient vector is what it is, right, at that point. So all it really, if we want to maximize that expression, all we need to do is to figure out how to maximize the cosine of that angle. Right? That's really the only part of this calculation here. Cosine of the angle is the only thing that isn't constant. So how do you maximize cosine theta? And think back to high school trig class. What value of theta makes cosine as big as possible? 0. Right, so theta equals 0 is the right answer here. So going back up to the picture then, what vector would have theta equal to 0? Well, theta is equal to 0 means that instead of that vector, we would look at that vector. So the unit vector, not just some arbitrary unit vector pointing to nowhere, the unit vector pointing in the exact same direction that the gradient vector points. That's the answer to this question. Said differently, the gradient vector always points in the direction where the function's increasing the fastest. That's kind of cool, right? I mean, that makes a geometric feature of the gradient vector, namely, what direction does it point? Natural. It's the answer to a reasonable question, namely, which way is the direction of fastest increase? Which way is uphill? Right? Gradient vector is the answer to that question. So very cool that the gradient vector is the answer to a natural and interesting question. And that makes the gradient vector natural and interesting. Okay, now let's ask a related question. Oh, side note, the unit vector pointing in the direction of the gradient vector. Don't forget how to compute that. Right? You take the gradient vector and divide by its own magnitude. That's, again, an old trick from chapter 1. Oh, let me also introduce another term. I personally prefer the term direction of fastest increase. But there is this probably more common term, direction of steepest ascent. And this goes back to the graph metaphor. Again, if you're thinking about the graph of some function, two-variable function, you can think of uphill as it being a way of describing the direction where the function is increasing the fastest. Height is the value of the function. So direction of steepest ascent is one way to think about what we've just computed here. Again, I don't personally prefer this term because it relies on the graph metaphor. If you have a function of 3 variables, let's talk about, again, temperature in this room. Right? That's a function of 3 variables, x, y, z. And at a certain point, there's a temperature. I very reasonably might want to know, if I were at that point, which direction, let's not talk about speeds, but in which general direction would I go if I wanted the temperature to increase as fast as possible? Well, you can't talk about the graph. There is no steepness. The graph of that function would be a 4-dimensional picture. I can't draw it, and it's a bad metaphor for that particular example. So nevertheless, direction of fastest increase still makes sense. But be aware of this term, direction of steepest ascent. But in your minds, I encourage you to think of it as direction of fastest increase. Okay, right. Related, next question. So we know the best direction. We know we're not going to do anything silly like that. The direction of fastest increase is that direction. It's the direction that the gradient vector points. Obvious next question. Oh, well, okay, so if that is the direction that the function's increasing the fastest, how fast is it increasing? That's the best one? That's the maximum value? What is that maximum value? Let's compute. What is that unit directional derivative? How fast is the function increasing? Well, that's how we compute directional derivatives. We just got through agreeing that that unit vector, that best unit vector, is the unit vector pointing in the direction of the gradient vector. So that turns into that. Gradient dot gradient is gradient squared, magnitude of gradient squared. So altogether I have magnitude squared divided by magnitude, and that gives me magnitude. So weirdly, the other geometric feature of the gradient vector, also interesting. The direction of the gradient vector is the direction of fastest increase. The magnitude of the gradient vector is how fast the function's increasing in that direction. Again, going back to the graph metaphor, how steep is the mountain? Well, the magnitude of the gradient vector tells you how steep the mountain is. Obviously in that direction of uphill. So I think it's really nice how these kind of turn out so conveniently. Both of the geometric traits of the gradient vector are natural, geometrically natural. The direction of the gradient vector is the direction of steepest ascent. The length, the magnitude of the gradient vector is the rate of change in that direction. So this is what we were kind of hoping and expecting would happen, is that we would be able to look back because of this observation, because we were relating the gradient vector to a dot product that we have cool information about. We were hoping to draw geometric conclusions about the gradient vector, and we did. Right? These are they. Gradient vector is very geometrically natural. Let me pause for questions. Everybody happy? Okay. So there's one more cool geometric interpretation of the gradient vector. It relates to level sets. So again, now, this very importantly, don't think about the graph context here. Right? We're not going to be thinking about graphs in this next calculation. Forget graphs. We're talking about level sets. So think about level sets of the function in question, not the graph of the function in question. Wild fact, it turns out that in the domain, so let me draw a picture here. We've got a function, some function f. Again, it's real valued, so one output variable there. Looking at a particular point, at a particular point, well, that point is going to be on a certain level set. Right? In other words, there's a certain value of the function at that point. Oh, let me do that in purple. That point has some value, and that value has a corresponding level set, and that point is on that level set. Another thing that you can do at that point is ask, what is the gradient vector at that point? So at that point A, there are two sort of existing mathematical objects that we've talked about that associate to that point. There's a level set going through that point. There's the gradient vector at that point. And the amazing fact is that those two are always perpendicular. Orthogonal. So really surprising fact. Again, you wouldn't expect right off the bat for them to be related at all. We've defined them in very, very different ways, but they are very strongly connected like this. So I want to show you why this is true. It turns out it's not such a hard proof. Maybe I'd better not delete that. Not such a hard proof. I'm going to come down here. The same picture. So got a point, a certain level set, and we've got a gradient vector. Right. So I want to consider now a path on the level set moving through our point. All right. Now this is a special path. I'm entirely confined to this surface that is the level set. And the point A is on that level set, and I just want to make sure that that path, as it moves along, passes through A. Okay. And I want to talk about the value of f as I move along that path. So let me write this down. I want to talk about, pencil. What is the value of the function f on these points x of t as I move along that level set. Okay, does everybody see what I want to talk about? Now, what can we say about these values? At any given time, wherever I should happen to be, well, x of t, this path, keep in mind, by assumption, the path is on the level set. So the value of the function, which I've written this in green to connect it to this picture in green, which indicates a level set, the value of the function is c. This, this is just an algebraic way of saying that the path was defined to be on the level set. So what does that mean? Now let's ask, how does this change? What's the derivative of this? I'm going to take the derivative of both sides. The derivative of f of x of t is equal to the derivative of c. Conveniently, the derivative of c is 0. Constants. Derivative of constant is 0. So what that means is that derivative is equal to 0. Fine. Again, not a surprising fact. Another way of saying that it's constant is saying that its derivative is 0. The cool thing about this is that this object I can interpret as a directional derivative. Right? This is a way of saying, look, I'm at this point A. I'm moving along a parametric curve. Namely, I'm at a particular point and moving with a certain velocity. And when I'm at that point and moving with that certain velocity, I want to know how fast the function's changing. This is said in a different way, but this is exactly asking, well, what's the directional derivative? Well, the directional derivative is 0. And if the directional derivative is 0, keep in mind the directional derivative can be computed as a dot product with the gradient vector, and that means that the gradient and the velocity vector are perpendicular. Does that make sense? Everybody on board? Cool calculation. I like the fact that we look at a picture one way and then we sort of reinterpret in a different way and get a powerful result. Okay. So last little observation: if the gradient and the velocity vector are perpendicular, coming back over to here, the velocity is perpendicular to the gradient. Notice that velocity vector could have been any tangent vector. So that means that the gradient vector is perpendicular to every tangent vector to the surface, and therefore it's perpendicular to the surface. That make sense? Everybody happy? So we've got a few examples here. Already zoomed out. Okay. All right. So here is a multivariable function. This might look familiar. We saw this back in 4.3.1. This was our first example of a directional derivative. Let's ask the question: how would I compute this directional derivative where I am at this point and moving with that velocity? Okay, well, we did it sort of the hard way. We did it the brute force way in section 4.3. Here, I'm going to rewrite that directional derivative as gradient dot vector. Computing the gradient is easy. Gradient is just a vector of partial derivatives. These partial derivatives are really easy to compute. Plug in the point that we're at. We're at the point 120. Easy algebra, easy arithmetic. And the velocity vector, here let's do this. And that velocity vector is what I dot it with. And easy arithmetic. And we get the answer you might recognize from back in 4.3. Okay, so gradient vectors are an alternative way of computing directional derivatives. Again, of course, this is just a sort of a variation of using the Jacobian matrix, which requires that the function be differentiable, but as a polynomial, of course, this definitely is. Okay. Okay, so in that previous example, in what direction is the function increasing the fastest? What's the direction of fastest increase? What's the direction of steepest ascent? Well, again, without the gradient vector, this would have been a hard question, but we know that, in fact, this is a question where we already know the answer. The answer is whatever's the direction of the gradient vector. Well, we computed the direction of we computed the gradient vector in the last example. Right? That's the gradient vector. The best unit vector direction is just the unit vector pointing in that direction. So I just take the already computed gradient vector, divide by its magnitude, done. Right? You should look forward to these questions on an exam. Here's a function. What's the direction of fastest increase? Because it's a simple little algorithm. You write down the gradient vector divided by its magnitude. That's all it is. Okay. All right. Okay. Now here's an interesting question. Like this. Let's look at this function. Now, note that's a function from R3 to R1. It's a function of 3 variables. If I were interested in a level set of that function, now this is a function of 3 variables, so a level set of this function is a surface, right? It's a surface in space. If I wanted to find a tangent plane to that level set, how would I go about doing this? And again, right off the bat, seems like maybe kind of a hard question, but keep in mind, let's draw the picture here. And I have no idea what this level set actually looks like, so I'm just going to draw arbitrarily some surface. It doesn't really matter. This is just for conceptual purposes. So at a given point, if I'm looking for a level set, what I'm looking for is something which, at that point, is parallel to the surface. Well, I know that the gradient vector of this function is perpendicular to the surface. Therefore, the gradient vector is perpendicular to that tangent plane that I'm looking for. Therefore, I can use the gradient vector as a normal vector for the surface. I can just call that in, and that's my normal vector for my tangent plane. Everybody good? Now, of course, I also need an x naught. Well, there's a free given point there that we know is on the tangent plane. Namely, it's the point where the plane is tangent to the surface. So there's your n, there's your x naught, and it's a little bit of algebra. So here's the gradient vector. Plug in the point in question. So that ends up being what you're going to use as your gradient vector. Excuse me, as your normal vector. So first, second, and third components there. That's what you dot with x, y, and z. Whoops. Z. There we go. There's your equation of your plane. Questions? Everybody happy? Yes?
As a question, so where are you looking for equation of the tangent and you have the normal to the tangent, right?
Yeah.
And it's three variables.
Yes.
The 3 input variables.
That's right.
And you want the negative reciprocal of that. How do you do that?
Want to what?
Negative reciprocal, like the way you do in single.
Oh, well, so yeah, so the negative reciprocal trick is used if you have if you're looking at the equation of a line, and if you know a tangent vector to the line, but you want a normal vector to the line, then that's where the negative reciprocal comes in. We have no need for such a thing here because the vector that we came up with in the first place isn't tangent to what I'm looking. It's already perpendicular, right? So we have no need for such a trick. If we were to, at some point to have such a need, it would be a little bit different because being in 3 dimensions instead of 2 dimensions, there's not just a single vector that's perpendicular to a given vector. There's lots of vectors that are perpendicular to a given vector. So we'd have to look at the other details of such a scenario. But it doesn't really come up as a problem here. Yeah. Yep. Okay. Anybody else? All right. Okay, so that's the gradient vector section. We're going to move on now, talk about the chain rule. I want to remind y'all first about the single variable chain rule, and I know you already know the single variable chain rule. Again, the purpose of this little intro I'm going to give is not to teach you stuff that you already know. It's just that I want to set it up in a certain way. I want to sort of frame it a certain way that will generalize nicely into the multivariable setting. So here we go. We have a composition of functions. We've got a function f with a domain and a target. And whatever comes out of f, I want to put in to g, g having a domain and a target. Okay, so we have these two functions, f and g. What comes out of f is what goes into g. And the chain rule is a way of studying, in a certain way, the composition. Right, it's what you get when you take the input to f and then look at the output from the subsequently applied g and view that as a single function. So if f takes x to y, if g takes y to z, the composition, g compose f, takes x to z. All right. Now, you guys, I know, already know the chain rule, single variable chain rule, and the chain rule is a way of studying the derivative, in particular, of that composition, right? And various formulas that you guys know how to write down, etc. So, here's the way I want you to think about that single variable chain rule. Remember, we can interpret derivatives as in different ways. I want to think about it in particular as a factor. So even in single variable context, I can think about the derivative of this function f as the factor that you multiply by an input change to get a corresponding output change. Rate of change, approximate change, whatever. Okay. So don't think of it as a slope, right? Think of it as and don't think of it as a fraction. Think of it as a factor. Okay, so f prime is what you multiply by what I have labeled here as the little v. Thinking of it as a vector, but it's a vector in R1, so it's just a number. So I'm not drawing it as a vector, but think of it as a vector. So the derivative is what you multiply by v to get w. Good deal? Everybody happy? Right, and so likewise, the derivative of g is what you multiply by w to get u. Okay, and then the derivative of the composition is what you multiply by v to get u. Right, fine. So let's write down the three different derivatives in question here. We have the function f, the function g, and the function g compose f. Three different functions. There are three different derivatives. Let's write down what we know about them. Again, thinking of them as factors. So to start off, f prime. Oh, let me do this in the color. F prime is the factor that you multiply by v to get w. Now, that's just representing what we already talked about here. Looking at that function, f prime, the derivative of f, is what you multiply by v to get w. Right? Okay. Now, a little detail. Where would I evaluate? At what? I mean, f prime is a function, so f prime evaluated where is what I multiply by v to get w. Well, f in this little scenario here is being evaluated at that point, a, and so it is at a that f prime is evaluated. So f prime of a specifically is what you multiply by v to get w. And you'll notice that here it's f prime of a. Okay? Likewise for the composition, the function g compose f, its derivative is what you multiply by, what you multiply by v to get u, the derivative of that composition. Where is the derivative evaluated? It's evaluated at the same point that the composition function itself is being evaluated, namely at a. So, derivative evaluated at a. All right. Okay, now you got to be careful with this next one. There's a little curveball. When I look at this function, the derivative of g is what I multiply by w to get u. Right, so derivative of g is what I multiply by w to get u. Fine, no problem. Where is this g function evaluated? Well, g is evaluated at that point, f of a. Got nothing to do with a. Right? So importantly, G is not evaluated, G prime is not evaluated at A. That doesn't make any sense. G prime is evaluated at F of A. And that's why, whoops, my color wrong. That's why this is there. So now, so we've made 3 observations about derivatives. Notice that I can put this formula for W there, and that gives me this turns into this, because that W turned into that. All right, is everybody on board? And what I've got then is one formula relating U and W. Excuse me, I circled the wrong one. Sorry. One formula relating U and V, and now here's a different formula relating U and V. And in particular, then this factor and this factor must be the same. Right, so the derivative then of the composition, G compose F prime is equal to G prime times F prime. Oh, now G prime being evaluated at F of A, of course. F prime being evaluated at A, of course. Okay. So now old news. I know you guys know the single variable chain rule. I just wanted to establish a way of thinking about the chain rule, because this point of view, thinking about this relationship between compositions, thinking about the derivatives as being factors that you multiply by input changes to get output changes, is what's going to generalize nicely to our multivariable setting. Before I go to that multivariable version of this, let me just make a sort of a silly sort of an easy observation. I wrote down a bunch of algebra there just to be rigorous about it, but I think it's pretty persuasive to say that, look, if this F prime is a multiplication by a factor, and if subsequently this is multiplication by another factor, what happens if you multiply something by 2 and then multiply the result by 3? Well, altogether you multiply by 6, right? So the idea that factors multiply is actually pretty straightforward, pretty intuitive. Does that make sense? So algebra aside, that's a great way to think about what's happened here, is that factors, when you compose factors, you're multiplying those factors. And that's why the derivative of a composition is the product of the 2 individual derivatives. Okay, that's a way of thinking about it. Right, fine. So let's do the multivariable version. You'll notice this picture looks pretty similar. We have a function f. Now it's a multivariable function f, domain and target. The derivative of f relates input changes to output changes. Okay, just like in the single variable version, it's just 2-dimensional now instead of 1. G is a multivariable function, and the derivative of g relates input changes and output changes. Okay, just that, again, now these are 2-dimensional vectors instead of 1-dimensional vectors. And then likewise, the composition input changes, output changes are related by the derivative. Okay. So you can write down the algebra just like we did before. But let me just argue sort of in terms of thinking about, what we sort of analogous to the very last observation I made in the single variable case. If the derivative of f is what you do to that vector to get this vector, and if the derivative of g is what you do to that vector to get that vector, then altogether the derivative of the composition is just going to be sort of the composition. First you're going to do whatever this is, and then subsequently you're going to do whatever that is. That's how you get from this v vector to this u vector. So you can look through the algebra if you'd like, but there's a expected punchline, and that is the derivative of the composition. Actually, let me zoom in on this. The derivative of the composition, in other words, the thing that you do to get from the first vector to the last vector, what you do is first go from the first vector to the second vector, and then subsequently go from the second vector to the third vector. In other words, the entire process of left to right is left to middle followed by middle to right. It's just that now, instead of those processes being multiplying by certain factors, now we're applying certain linear transformations, these derivative transformations, but the composition nature of them is still the same. Okay. So, really great result. That this is the chain rule, by the way, the multivariable chain rule. This is a version of the multivariable chain rule. That the derivative transformation of a composition of functions is the composition of the individual corresponding derivative transformations. Now, good news. Is this all? No, not quite. Zoom out a notch here. Derivative transformations are represented by matrices. Oh, I guess I'll do this one. These derivative transformations are represented by Jacobian matrices. Composition of transformations is represented by matrix multiplication. Flashback to chapter 3. Composing linear transformations means you multiply their corresponding matrix. That was kind of in some sense, our definition of matrix multiplication. So an alternative and really kind of more day in and day out practically useful version of the chain rule is this. Is that these matrices that we write down, these matrices of partial derivatives, the Jacobian matrix of the composition is the product of the individual Jacobian matrices. Okay. All right. Let me pause for questions maybe before I do some examples. Great. Let's see some examples. Right. So now I'm going to start off with one that's fairly abstract just to kind of get the ball rolling. In other words, I'm not going to tell you what these two functions are. I'm just going to say, suppose we have two functions that we're composing. So in particular, we have f that goes from R2 to R3, and then we have g that goes from R3 to R3. And notice that I'm given the corresponding Jacobian matrices. This is just given to be the Jacobian matrix for F, and then this is given to be the Jacobian matrix for G. So this is, like I say, is kind of a sort of a softball. I'm giving you exactly the two matrices that you need that describe the derivatives individually of these two functions I'm composing. Now, a quick note. Notice that I'm given that f is being evaluated at the point 1, 2. So I'm specifically giving you the Jacobian of f at the point 1, 2. Note that g is being evaluated at the point. G is being evaluated at the point that comes out of F. The point that comes out of F, I should use a different color for this. The point that comes out of F, therefore the point that goes into G, is the point where I'm giving you the Jacobian of G. So I'm giving you exactly the two matrices that you need. Right? This is all just on purpose, so that just to keep life convenient for the beginning. And the question is, what's the Jacobian matrix for the composition? And then more specifically, how would I compute this particular partial derivative of that composition? We'll come back to the second part. Start off, how do I find the Jacobian matrix of the composition? Well, the Jacobian matrix of the composition is this product. It's the Jacobian of G left. We're just going to multiply those two matrices like so, and that gives us our answer. Now, it's straight up application of the chain rule, the matrix chain rule that I just gave you. Now, let me point out a really awkward thing about how the algebra works out on this. Lots of students fall into trouble on this. This is a really dangerous little fact. I have a little personal story I'll share after I tell you what the problem is. It kind of looks like the functions got written down in the wrong order. Did y'all notice this? I went through it deliberately quickly, but there's a really dangerous fact. Notice that in this diagram here, F acts first and is therefore on the left because we're drawing things left to right. And then G acts second and therefore is on the right because we draw the diagram left to right. So F is on the left, G is on the right, except for the fact that when I come over here, I multiplied them in the opposite order. The Jacobian matrix of G was on the left. The Jacobian matrix of F was on the right. So is that a mistake? Did I do it backwards? Did I oops this? No, this is right. Tragically, if you just kind of think it through, the notation that we have for how we compose functions, when you write down, this composition, that composition is written as G compose F. Blue is on the left. What's on the right in the diagram is on the left in the notation. What's on the left in the diagram is on the right in the notation. Sadly, by the way, it kind of has to be this way. Because let's look at how we evaluate such a thing. How would I evaluate this composition? Well, if I had some x going into this composition, note that F acts first, G acts second. So when I'm evaluating the composition, let's see here, I have to say G of F of X. Because F acts first. So F kind of has to be next to the X because it's doing its thing first. It's just unavoidable in the way we write functions, right? Arguably, if you want to ask, where's the guilty party? Who messed this up? Who created this little disaster that we're dealing with? Arguably, it's the idea that we write the function sort of on the left side of the number that we plug into the function. Because look at our diagram. In the diagram, the number that goes in is on the left. We draw diagrams left to right. It's deep in our culture, right? So why are we writing the function on the left over here? So anyway, it is what it is. Okay, well, this will never change. So you just have to be aware of the awkwardness, right? And be very, very aware. Now, the personal story I wanted to share on this is that I made a mistake on this. Happens to the best of us, right? It was related to it was for morally the same reasons. It was a different algebraic object. This is while I was working on my PhD way back when, and it was part of a calculation that took me a month, and I got an answer that was highly implausible at the end. And so I traced back through and found that I had made, morally speaking, this mistake. I put them in the wrong order because I just wasn't thinking carefully, right? And so I had to take an entire month's worth of calculations and throw it in the trash can, right? So I do not make this mistake anymore, right? You get stung that bad and you learn your lesson. So I implore you, please do not learn as I did in the School of Hard Knocks on this. Make sure to think very carefully about which way it goes, right? When you're writing these things down, think it through the right way. And again, in particular, notice that the function that acts first is on the right because it has to act on the vectors that it acts on, which are on the right. It has to act first, so it has to be written then on the right. And the one that acts second has to be on the left. Everybody on board? Everybody happy? Think it through. Be very careful. You've been warned. Okay. Right, so moving on. So now the next part of the question was to compute a particular partial derivative. Now, notice we don't know what these functions are, so I can't just compute the partial derivative sort of directly, but I can observe what the variables are that we've got here. So we've got, bad color choice. So we have these input variables, x1 and x2. I don't really have or need any names for these variables in this particular example. The outputs, g1, g2, g3. And note what the question has asked for. The question has asked for the partial of g3 with respect to x1. So I want the partial of that with respect to that. And remember how Jacobian matrices are constructed. Jacobian matrices are constructed in a particular way. The columns correspond to the input variables. So since we're looking at a partial with respect to the first input variable, we want a number in the first column. We want to know the partial of the third output variable. That means that we're going to be looking in that first column at the third entry. Said differently, third row, first column. Which is that number. So that partial derivative is 3. Everybody good? Right, so moving along. I'm going to give you a different point of view on the chain rule. Let me start by rewriting the chain rule a little bit. There it is. Now, this looks like a nightmare. I think we can agree, right? That looks like a nightmare of inconvenience and difficulty. All this is, though, is the multivariable chain rule written with coordinates. So altogether, what we have is a composition of functions. Let me put this up here. I have from Rn to Rm is the function f, and then from Rm to Rp is the function g. The Jacobian of f is that matrix. It's the partial derivatives of x1 through xn, with respect to x1 through xn of y1 through ym. So let's take a moment and notice that all of this nasty here is just representing the Jacobian matrix. One Jacobian matrix. Likewise, z1 through zp and all of this nasty is just the various entries in this single Jacobian matrix of the z variables with respect to the y variables. Right? And so then this matrix, being the product, therefore being the Jacobian of the composition, is the partials of the z variables with respect to the x variables. So altogether, it's just the chain rule rewritten and sort of expanded out, sort of full ugly. Right? That's all it is. Okay. Now, having made that observation, let's ask a question. Let's focus our attention on a particular entry in this matrix, and it doesn't matter. I'm just going to circle this one just to have something to point to. How would I compute that particular entry? Well, we know how to multiply matrices. We have a lot of experience with multiplying matrices. Specifically, I take the corresponding row of the first matrix, the corresponding column of the second matrix, and I do a dot product. So there's those various green entries. There's these various blue entries. So what I have written down here is nothing more than explicitly doing the dot product of the appropriate row with the appropriate column to get the entry in question in the composition Jacobian matrix. So what this gives us then is a different point of view on the chain rule. So I can think about the chain rule instead of thinking about it sort of in matrix form, instead of thinking of how it's a composition of matrices. Statement about multiplication of matrices. And instead of thinking about it in the even uglier form of multiplication of matrices, I could instead think of the chain rule as this little formula here. Well, this formula here. Not that little, right? So I want to walk you... Oh, I am out of time, aren't I? Shoot. Okay, starting next time, I will walk you through an intuitive way to think about this equation that actually is pretty natural and pretty useful. Okay, see y'all later.